A Lewis structure for a molecule is two-dimensional. It's what you can draw on paper. It shows the atoms and how they're bonded. We'll start with the Lewis structure in order to understand the three-dimensional molecule shapes. In these examples, there are bonds that are single bonds. A single bond is a single line. There are also bonds that are double bonds, and those are two lines, and those are all bonding pairs of electrons. There are also non-bonding pairs of electrons, and those are called lone pairs. When electrons are shared in a bond, it's called a covalent bond. We can convert the two-dimensional Lewis structure to a three-dimensional molecule shape that's called a VSEPR shape by looking at how many bonds and how many lone pairs are on a central atom. So this is called VSEPR theory, VSEPR standing for valence shell electron pair repulsion. You have a central atom and other atoms bonded to a central atom. Those atoms all have electrons on them, and electrons are negatively charged, and they all want to be as far apart as possible. That's because like charges repel. So that's this electron pair repulsion, and it's the electrons that are on the outer edges of these atoms. Those are called the valence shell electrons. These electrons are the ones that interact with other atoms' electrons. We'll look at this for several molecules, the first being this methane CH4. So this has a carbon with 4 single bonds. So those are 4 single bonds on a central atom. When there are 4 single bonds on the central atom, all those bonds have electrons and they all want to be as far apart as possible in three-dimensional space. So in two-dimensional space, this looks like a box, a square. Well, in 3 dimensions, you can bust out into the front and the behind of the paper, leading to this, which is called a tetrahedral shape. The tetrahedral shape is a tall pyramid. It has a base of 3 with a tall top, like a tripod. Methane is CH4. And we started with methane, the name, and this is the chemical formula, CH4. It's the first in the series of hydrocarbons. Remember, mother eats peanut butter. So there's 1 carbon in that. This is the Lewis structure of methane. It has a carbon with 4 bonds. Every hydrogen has the duet rule fulfilled and the central atom. The carbon has the octet rule fulfilled, and that's what drives the bond formation. And from the two-dimensional structure, there are 4 bonds around the central atom, which forms a tetrahedral shape. This is the tetrahedral shape, which is the more accurate shape in 3 dimensions. You've got 1 atom up as the tall top, and then you've got a base of 3. This is called the molecular view. It's also called a space-filling model, where this shows the atoms as colors. Carbon's typically shown as black and hydrogen's as white, and this is the molecule in its truest form. You have the atoms smushed together because the bonds holding those atoms together are covalent bonds where electrons are shared. So the atoms no longer have their own electrons, but they're sharing them, so they no longer have their own boundaries. In order to get to this space-filling model, this is the molecular view, you have to go back to the chemical formula, which then builds the structural formula, also called the Lewis structure. From the Lewis structure, the number of bonds and lone pairs on the central atom will give you the VSEPR shape. And the VSEPR shape is the 3-dimensional shape of the molecule. Lone pairs of electrons are important in VSEPR theory because they take up more space than bonding pairs of electrons. So in this example, this is ammonia, which is NH3. Here's the Lewis structure of NH3, and this NH3 has a central atom of nitrogen with 3 bonds. Those are 1, 2, 3 bonds and 1 lone pair on the central atom. When you have 3 bonds and 1 lone pair, these 3 bonds don't space out equally because of the lone pair electrons. It basically causes a base of 3 with a low top, which is not seen. It's this lone pair of electrons, which would be here, and you just have the base of 3. This is the bottom half of the tetrahedral structure. It doesn't have the tall top, and this is called trigonal pyramid. It's a low pyramid compared to the tetrahedral that's a tall pyramid. This is the space filling model. This is the molecular view of ammonia, where you have blue for the nitrogen and then 3 white hydrogens. So this is a base of 3, which are the 3 hydrogens, and then this slightly above it is that nitrogen. So this is the trigonal pyramid shape, a low pyramid. The Lewis structure of water is very symmetrical. It has a hydrogen on either side of the central oxygen, and then a lone pair of electrons on top and bottom of that central oxygen. Well, when you take that 2-dimensional shape and convert it to the 3-dimensional VSEPR shape, water is no longer linear. It's not linear because those lone pairs of electrons force downward those bonds to the hydrogens, and you end up with what's called a bent or V shape. In this bent or V shape for water, you have the oxygen central atom is shown as red on the space filling model, and there are the 2 white hydrogen atoms are down on the bottom of the V. But you could flip this up and it would be a V like this shape. So the bent shape is bent because of the lone pairs of electrons that take up more space. Lone pairs of electrons have an effect on the 3-dimensional molecule shape and the molecular views and space-filling models that you can see. The lone pair of electrons on this ammonia, this one pair, forces the 3 bonds downwards into the low pyramid shape instead of, say, spacing evenly out into the trigonal planar or a flat triangle. There are 2 lone pairs on the oxygen atom of water. That's the central atom. And those 2 lone pairs are not symmetrical above and below the oxygen. The lone pairs on the central atom of oxygen force those bonds away as opposed to spacing out evenly. It's linear, and that's how you end up with the bent VSEPR shape. So you'll be looking at how many bonds and how many lone pairs on a central atom to determine its VSEPR shape. Although the Lewis structures show single bonds, double bonds, and triple bonds looking differently, there's 1, 2, or 3 lines, in 3-dimensional shapes, in the VSEPR shapes, when talking about how many bonds are on a central atom, it doesn't matter if they're single, double, or triple, because all those bonds are just connections. So you'll be looking at how many bonds, how many sets of lines are coming out of a central atom. It can be a double bond, which is considered 1 bond. It can be a triple bond, which is considered 1 bond. And those bonds mean connections of a central atom to an outer atom.